So one of the goals that we'll finish up in this video is looking really briefly at some key points in spectroscopic analysis, and then we'll move on to chapter 23, which looks at the reactivity of the enol and enolates, which is kind of an interesting chemistry. First off, your carbonyls. What you would expect to see in the IR is a really strong peak about 1700. You'll notice this is kind of a popular question to ask, the relationship between these two structures. They both have a carbonyl, and while you might not be expected to tell a difference between those carbonyls in an actual spectrum, what they would ask is which of these has a lower frequency. The frequency of all signals will shift to lower values when they're conjugated with some other pi system. So in this case, if we take a look at that carbonyl, we have an alpha beta. We'll talk about what alpha beta means in a little bit. An alpha beta unsaturated ketone. That unsaturation happens to conjugate within the pi system, and if you go through and look at resonance, we can weaken that bond. Well, if the bond gets weaker, it shifts to a lower frequency. Okay. The other kind of important thing to look at or look for is that aldehydes will give you another set of peaks, about 2700 and 2800, right below the CH stretch for sp3s. The characteristics here is coming from the fact that you do have a CH in the aldehyde, but it's kind of a weird one. That carbon is sp2 hybridized, so we might expect above 3000, except that oxygen is so electronegative that it's drawing so much electron density away that it actually weakens that CH bond. So it actually shifts again to a lower frequency. So it's something, and it's fairly characteristic. You should see it there, about 2800. When we look at NMR, a couple things pop up. We can't see the carbonyl directly in HNMR, but if there's an aldehyde, we will see the aldehyde hydrogen, and that shows up again really characteristically at about 10 ppms. So if you don't remember that, you'll need to review that information. There's a spectroscopy video posted, so I'll try and reference that in the link or in the comment section below this video so you can find it. The other thing that you could look for is in the carbon NMR, a carbonyl carbon is also fairly characteristic. It shows up about 200 ppm. There's really not much else that would show up out there. So if you've got that carbonyl, you should see it popping up in the carbon NMR. So you've got a variety of places that you could pick up on your spectroscopy. So real quickly before we get into chapter 23 too much, this concept of alpha and beta, because chapter 23 looks at this in extensive detail. What we're looking at is now kind of a secondary effect. How does the carbonyl affect the other positions nearby? And in almost all of our other reactions, we kind of ignored those positions, for a certain extent. You think back to our alkyl halides. Our alkyl halides weren't just, looking at chemistry at our carbon where the chlorine was attached. We also looked at chemistry over here, right? Because we could do an elimination reaction. So we see something very, very similar with our carbonyls. They do happen to affect the chemistry of other positions. And just like with our alkyl halides, having that hydrogen there, we do have the potential to do some kind of elimination reaction. So that alpha position is directly acidic. Okay. And acidic enough that we can get some sizable reactions happening due to pulling that hydrogen off. And that's where a lot of the chemistry in 23 is centered. The other thing we'll look at well, actually, let's go through and say what that chemistry is. It's acidic, which then turns that carbon, there's a reason for switching the color, into a good nucleophile. Okay. So we can get that kind of secondary, tertiary chemistry out of it, if you want to look at it that way. Our primary being the carbonyl, our secondary being that alpha proton is acidic, which then makes the carbon a nucleophile. So we've got a couple tiers of chemistry coming out of this. The beta position becomes reactive really only after we've added an extra functional group. And that extra functional group happens to be a pi bond. So if we have that pi bond, so if pi, and we have this alpha beta issue, so it would typically be called alpha beta unsaturation because we don't have hydrogen at that point, then the beta carbon is electrophilic. Okay, and I will be asking you to kind of play around with mechanisms a little bit and prove to yourself that you can see these things. It does take a little bit of time, but you guys should be able to do it. So those are going to be some of the new nomenclature-ish sort of things that we're going to be referring to. This alpha and the beta position, and you need to watch out for that chemistry and see what happens when it's activated. And there are all sorts of conditions that go along with these. Realize that we will end up still potentially forming acetals and hemiacetals and all sorts of other fun stuff like that. But typically in equilibrium, and we tend to ignore those effects because we aren't focusing strictly on those. So be aware. There's our big summary. Got everything on it. I'm kind of suspicious that I'm missing something, so I actually don't think this has everything on it from chapter 23. But it's got a significant amount of it on there. And it really all starts in the dead center of this. So we're going to look today, or in this video, at the chemistry, kind of sitting right in the middle. What's happening with it, with ultimately our alpha position. So there's our alpha hydrogen, and how that can change the chemistry of our carbonyl. And then ultimately what we'll do is look at how it reacts with halogens. There's a couple key tests that you need to watch out for within both of those, but for the most part it's fairly straightforward. You probably won't see the halogenations all that much. After that, we'll end up looking at all those other reactions. I haven't quite decided the order that will go with those, but each of those is a particular class of reaction with all sorts of other fun things that can happen with them. So it's kind of neat. So, enols and enolates. You may be thinking, oh my god, not another new functional group. Well, it's actually not a new functional group. We've seen this before with our alkynes, particularly in the presence of our mercury or boron for that matter. So the reagent that actually listed up there was kind of an unfortunate side effect. This is from our alkene chemistry. But what's listed in the reaction is correct. That's what you'd see for your alkynes. So take a minute here. I'll give you about a 10-second pause to predict your product of this. Okay, so hopefully what you remember, either from looking at the actual reagent or our alkene reagent, is that what these go through and do is add hydrogen and OH across a pi bond. So what was a pi bond now becomes H and OH. Can only do it once though. So what ends up happening is, because this is symmetrical, you don't really care, we'd end up with our hydrogen and we'd end up with our OH and we have that little structure. Well, if you looked really, really carefully at that initial starting slide, what we have right here is the alkene and the alcohol, also known as our enol. Highly unstable, and when we dealt with this with our alkynes, that very quickly rearranges a little bit, and we end up with our ketone, okay, or our carbonyl. Yes, technically we have the option of it showing up on either side in this case because there is no real difference between those sides, or either side of that pi bond, but there is no difference between those carbons, so we don't have to stress about that. So, we have seen it. We know it's there. We just kind of sort of not talk about it in great detail, at least until we get up into this chapter. And really what we're going to now start to do is look at really what makes it different, okay, or what we can do with it beyond just, hey, it becomes a ketone. So, a couple conditions on how we can go through and make these without having to deal with our alkyne is we can start with our ketone or our carbonyl, because it works for aldehydes as well. Works for aldehydes. We can start either under acidic conditions or under basic conditions. And again, I think one of the later slides here is going to ask you to go through and come up with a mechanism on your own. And maybe in class, if you guys have questions, I'll walk through it. But under acidic conditions, we end up with the enol. And under basic conditions, we end up with the enolate. Okay, this 8 ending will start to look more and more familiar as we talk about our carboxylic acid functional groups. It's really, in reference to that negatively charged oxygen. And officially that pi bond too. But that's really all we're looking at. Okay? So as soon as we can make these, we then have some potential interesting chemistry coming out of it. And that interesting chemistry may or may not be obvious. So if you don't see it right away, what we should go through and do is draw resonance, because it's the same chemistry for both. So let's take a look at the enol. Our electrons can come crashing back into the pi system, and that would kick out electrons. Let's not do it quite like that. Kick out electrons onto our carbon, and we would end up with, in a resonance structure, this very unhappy Lewis structure, that negative charge. We now have our nucleophilic oxygen. Okay, there's our nucleophilic carbon. Okay, with that negative charge. You'll notice that we will never show that negative charge under acidic conditions. What will end up happening in our actual mechanism is we would start with our enolate, or our enol, we'd push the electrons down, and the pi bond comes out and attacks an electrophilic atom. Okay, so we would avoid showing that nucleophilic carbon in the enol mechanism because it's negatively charged, and that in general is kind of bad mojo. That said, we do have a resonance stabilized species, so it's not the worst negative on the planet, and if you really feel like showing it, feel free to go ahead and do so. I will also add with this that this species carries a special name. Okay, and everybody loves more names. So you might see this show up. We've got a species that has both a positive and a negative charge in it, and it is overall neutral. What we are looking at is the Zwitter ion. Zwit, I believe, is twin in German, something like that. So we have, the twin ions in our structure. So you might see that term, you might not. Don't stress about it. In the other case, with our enolate, you might immediately go, well, that oxygen is negative, it's got to be a nucleophile. It is technically negative, and it could potentially act as a nucleophile, but for it to act as a nucleophile, the electrons need to leave the structure, and there's a much better place for those electrons to go within the structure, so we end up not seeing our oxygen as a nucleophile. Okay, very rare circumstances is that can end up happening. But as it pushes back down, the electrons can then be put onto our carbon, and we end up again with a Lewis structure looking like this guy, very similar to the one above, except no zwitterionic species. And we again have our nucleophilic carbon. Okay? So depending on what we're trying to do, we may want to run under acidic or basic conditions. And that's going to depend on ultimately what our products are. So if you go back to that previous slide, you'll notice that in certain circumstances there is both the acidic and the basic option given. And under other cases it's almost always the basic condition. You should be primarily concerned about the basic condition being your functional one. We're really looking at that enolate form, that negatively charged carbon, really jumping out and saying, yes, I've got electrons, let me do something with it. So your base condition is your primary one. Okay? That's where you'll be spending almost all of your time when we go through and look at, go ahead and circle the nucleophilic characteristics, when we look at the reactivity for our enols or enolates. This whole process is referred to as a tautomerization. So another fun word to pop up. So you have keto-enol tautomerization, because you started with a ketone and you end with an enol. They aren't officially resonance, which you will hear people mistakenly refer to it as. I'm sure I included have done the same thing. It's not resonance because you've changed the location of a hydrogen atom. It's fine to move pi bonds, but you can't break sigma bonds. So that hydrogen was originally attached to your carbon. So we can't do that. And in the case of the enolate, we removed that hydrogen altogether. Okay, so you still can't do that in resonance. They aren't really isomers. At least the enol and the keto are isomers, but not the enolate. So we're kind of in this weird gray area of what to call them. Apparently someone liked the idea of Tautomers, so that's what we're referring them at. We will refer to them as Tautomers. So our enolate chemistry, we first need to make it happen. So go ahead and pick one of these and provide a mechanism for the formation of the enolate. Acidic and basic conditions work, so ideally you pick one to be acidic and one to be basic, and then go ahead and run with it and see what you can come up with. Because this is supposed to be the lecture that we're missing, in the activity that I build, I will give you a stepwise setup that doesn't solve the mechanism but gets you pieces of it, and you can insert your structures into it, and I'll ask some questions about it as well. So take some time, go through and draw this out. Once you think you've got it drawn out, we will go ahead and get started again. So I'll give you 5 seconds here to either pause or just wait it out. Okay, let's see, do I advance? I don't think I want to see those numbers quite yet. So if you went through and drew out your mechanism, we look at our tautomerization. I'm going to prefer the enolate form and put the negative charge there. We go through and with our aldehyde, we'll put our negative charge out here. So our aldehyde still works. It doesn't work quite as well. One reason being is that there's less hydrogens. Okay? We've only got one place that we can pull the hydrogen off of, an alpha position. The hydrogen that is attached to the aldehyde is pretty much non-reactive, so don't go pulling on that one. For the structure on our left, you'll notice that I pulled those red hydrogens, and I didn't pull hydrogens off of the end. Okay, those are possibles. Okay, we could just as easily have drawn those structures out. Okay, so I'm just going to draw one of them. There's our oxygen, and our negative charge. So kind of the idea is that we've got all of these possible things that can happen. Which of them are going to happen first or fastest or primarily? That becomes a little bit of a trickier question. So if we take a look at our first structure, okay, which of those two is the most likely enolate to form? Well, we got a lot of considerations that we could run through. We've got size. We could try and do a steric argument. We can do electronegativity. Ultimately, I'd say all of those answers are going to fail for us because what we're looking at is the stability of the most reactive thing, which is right here. And in both those cases, it's a carbon atom holding that negative charge. So we need to look beyond just an atom effect. That atom, beyond that atom effect, is looking now to resonance. In the case of our red structure, we've got resonance with the right oxygen, and we have resonance with the left oxygen. If we take a look at our blue structure, there's really only resonance with the rightmost oxygen. So what does that mean for stability's sake? Well, stability then suggests that our red enolate form is the more stable conjugate base. Well, if it's more stable, then the red one is the more acidic one. So what we're looking at is piecing it slowly together to decide which hydrogen would be most reactive. And so given the opportunity, we're going to pull off that red hydrogen first. This reagent is used very commonly, and we'll see it pop up again and again. So what we're looking at here is pretty much a diketone, and it really helps to activate those hydrogens to being extra acidic and really drive this reaction along. If we go through, and I'll erase our other choice, our aldehyde, remember I said that we don't really have an option with the other hydrogen, so it's not even worth drawing. We do have resonance stabilization. That resonance stabilization allows for the enolate to form. So kind of a good deal. So both of these have resonance. So we say, okay, well, they're both acidic. Well, which one's more acidic? As we already started to address, what we're looking at is the resonance effect. The one on the left has two resonance structures. The one on the right only has one. And if we actually quantify this and look at the pKa's, you'll notice the pKa for the dione is quite acidic. You're looking at a pKa of about 9. The pKa for the aldehyde, even in my opinion, is surprisingly acidic. It's at 16.7, so it's a little bit less acidic than water, but that's still pretty darn impressive when you think about our acid-base chemistry. So both of these can do some pretty standard, easy acid-base reactions. So what we'd be looking at is equilibrium effects in that tautomerization to decide which way we favor. Primarily, we're going to favor the ketone form, but if we can somehow get that nucleophile to react, we're going to see our equilibrium start to push and drift, and we'll be able to get more product coming out of our reactions. Another example I'll throw in here, the dione functionality or acidity is darn close to everybody's favorite functional group. The how was it suggested that I say this? No, I can't remember how to say it. It's the phenol. That phenol has a pKa of about 9 to 10. So we're looking at something that's quite acidic. I mean, you're getting down into that range of high acidity for organic molecules. Let's switch it up and look at an unsymmetrical ketone. So now we'll ask the same question, is which is more acidic? Which hydrogen is going to be pulled off? And this becomes also relevant because that's now going to change the reactivity of this. Because if we look at our enolates, we have a negative charge on the least substituted versus the most substituted carbon. It's going to drastically change where the next chemistry occurs because now our nucleophile is in a different spot, which means the electrophile is going to attach in a different spot. So we need to have some understanding of why we might go to one position or the other. And that's a bit more challenging. So what is our primary difference in this? So take a few seconds here, go ahead and look at it and see if you can't come up with an idea on which product you think is favored. And I will say this is going to go back to that topic that we came back to in Diels-Alder. So in the Diels-Alder reaction, you might be thinking, oh, exo and endo. No, not that far back. We're looking at kinetic versus thermodynamic. So what do I mean by that? Well, if we look at thermodynamics, it's the raw stability at the end of a reaction. So if we now compare these two structures, which of those is more stable? Well, to figure that out, you have to decide where's our difference. So we might say the alcohol, oh, the alcohol's more. Well, the alcohol's the same in both cases, so that doesn't work. Well, then the next move is to the alkene. And we look at the alkene. So, well, it's still an alkene, but is it the same activity alkene? Well, no, because in one case it has more substituents than the other case. So what we should be able to identify right away is that we have the thermodynamic product here. Well, if this one's thermodynamic, almost undoubtedly the other one's going to be kinetic. But let's go back to our transition states and prove why the top one would be our kinetic. So if we look at our intermediates, now floating through the middle, where's our highest energy thing there? Oh, look, it's already circled for us. It's that red negative charge. Where's a negative charge best held? On a primary, secondary, or tertiary position. Okay, if you got questions with that one, let's switch it up and say cation. So now ignore what's on there. Where's a carbocation, a positive charge, best found? On a primary, secondary, or tertiary carbon? Hopefully you've got tertiary carbon. Well, what's the relationship between a positive and a negative charge? Are they the same or are they opposites? Opposites, okay, so if a carbocation is most stable on tertiary, where's the carboanion most stable? Primary. So if we look at our structures, that topmost one is the best place to put our negative charge. It's got less electrons around it, it's a little bit happier. There's our kinetic product. Okay. So sure enough, we do verify that, our orientation between our kinetic and our thermodynamic. So now we'd want to decide where's our primary product going to come out of this. Well, this is all looking at equilibrium, and because these are all equilibrium reactions, we usually have to give it lots and lots of time, which means we're going to start to favor our thermodynamic product. So watch out for that. Almost all of our products are going to come out of this as our thermodynamic product, which can make things a little bit more challenging when we go through and look at situations. And if we wanted to, say, favor a kinetic result, we're going to have to change the dynamics of the reaction, which is something that we actually did in the lab. So, next part, choice of the base. So if we're going to look at doing our enolate formation, we're going to have to be very careful with our selection of base. When we look at the selection of acid and the acidic enol formation, it's not that big of a deal because we end up generating a nucleophile, so having a nucleophilic conjugate base for our acid conditions isn't really going to affect anything. So we aren't too stressed about that. But the choice of the base and the reaction and trying to make our enolate can be a bit more problematic. So what we want to try and go through and do is pick our base very carefully. So we've got 3 acid-base reactions shown below. So we've got 3 different bases. We've got ethoxide, we have hydride, and we have diisopropyl amide, so our LDA. So of these 3 choices, we may want to go through and use a different base. We need to have an understanding of why we might use one over the other. Okay, so take a look at them, see if you can't figure out some differences. Yes, there are some numbers tossed in there which might help you out. But yeah, think about it for a few seconds here. Okay, coming back to it, a lot of this is going to depend on where we're trying to go. What are we trying to do? So if we're looking at something that's going to involve a fair amount of equilibrium, and we don't really care about the strength of our base, mainly because maybe our starting material is changed around. Maybe we have something that's starting much more acidic. If we start with something much more acidic, then maybe ethoxide is a good choice. Because we don't need to use a really strong base. You will notice that the equilibrium does favor the reactants. So we'd be forming relatively small amounts of the enolate. So if we were going to choose this, we might be looking at a reaction that's going to involve a lot more equilibrium concerns. If we go through and look at the next two are really pushing extremely far to the right. In fact, we say pretty much no equilibrium in these cases. Both hydride and the LDA are such strong bases that they will go through and deprotonate and pretty much just leave it deprotonated. We cannot do the reverse reaction. In the case of the hydride, we can't do the reverse because we form hydrogen gas, and hydrogen gas then bubbles out of the solution, and there's now no acid to do the reverse reaction. With the LDA, we do still keep that hydrogen present, but the pKa difference is now so drastic that there's very little returning to our carbonyl structure. Okay, so that's kind of our balance with both of those. So if, for instance, we absolutely needed the enolate as our nucleophile, and we needed to do it as quickly as we could, we might pop out and drop in one of these stronger bases. Along the lines of those stronger bases, we've seen LDA, and that's usually added as, actually, how is that added? I think that's usually added as an L. Lithium, oh yeah, LDA. Lithium diisopropylamine is our LDA. So you'll see lithium as your counter ion. With the ethoxide, you'll probably see sodium as your counter ion. And then for the hydride, that one's a little bit trickier. We've seen hydride before, and almost everybody's going to go, oh yeah, sodium borohydride, lithium aluminum hydride. Problem with those is that those are not basic. Okay? Yes, they have some base characteristics, but particularly in the presence of carbonyls, they zero in on the carbonyl and will add the hydride to the carbon. So what we want is a non-nucleophilic source of hydride. That non-nucleophilic source, bit odd, is our sodium hydride. Primarily because sodium hydride has such low solubility in water, low solubility in organic solvents, that it stays pretty much as a solid. So we have a phase barrier that really prevents the reaction. So if we look at sterics, surprisingly, sodium hydride is almost incredibly bulky, just because it can't get in to react with anything because there's that phase barrier. So kind of weird, but that's actually kind of what's happening with it. So sodium hydride is really just a strong base and not much else. So kind of neat. So again, depending on what you're trying to do, you may be using or you may be seeing a variety of these bases pop up. You just kind of need to be aware of them. They're all pretty much driving to the same thing. It's just a question of how they go through and do it. Okay? So, our overall summary is that we can convert a compound into a nucleophile. So, it's a question of which atom becomes nucleophilic and how we go through and do this. So, our acidic atom is our hydrogen out here. Okay, under basic conditions, it's directly pulled off the structure, and we end up with our enolate. Okay, under acidic conditions, it's not easy to pull that hydrogen off unless there's a driving force. Under acidic conditions, we add H+, which then polarizes our carbon-oxygen double bond to the point that we can do that elimination reaction to form our enol. Okay, so those are kind of our overall ideas behind our keto-enol tautomerization. The rest of chapter 23 is really going to evaluate what possible electrophiles there are. So what we're going to focus on with the rest of this video is just our halogens, and then later videos we'll talk about alkyl structures, and then we'll look at our carbonyls. I will mention that our carbonyls, to me, probably get to be the most frustrating, because for some reason everybody's attached their name to one of the carbonyl reactions. So you'll get Michael additions, you'll get Robinson annulations, you'll get aldols, which I don't think is someone's name, but it's still a named reaction, if you will. You get a Dieckmann reaction, you get a Claisen reaction, and ultimately all of those are carbonyls acting as our electrophiles to some certain extent, and somebody just has to attach their name to it, even though it's the exact same chemistry as something that was already discovered. Okay, so be aware of that when we get into that section. So, our halogenations. So what we've got here is our nice summary, and we can go through and work with either the base conditions or our acid conditions and our halogens. The two most common halogens you'll see pop up would be bromine and iodine. We'll talk about the iodine because that's actually a special case that almost undoubtedly will show up. So what's happening is if we run under acidic conditions, the first thing that we would end up getting, and I'm just going to draw it out and not give you a mechanism again because I don't think mechanisms have been helping much. We would end up with our enolate. Make sure that doesn't look like a pi bond. Our enol, because we're under acidic conditions. And now what ends up happening is that our oxygen can still share electrons downwards and come out and attack. And what it will attack is our electrophilic bromine. Remember, our halogens are electrophilic because they are attached to an electronegative atom. But they do need to be relatively polarized, either by the solvent or by our nucleophile to actually initiate something. So it's kind of similar to what you saw with our EAS reactions. And we would now end up with, come on, pen's not working very well this morning, our halogenated product. Okay, we could then follow this up with, say, maybe a water workup, which will never, ever, ever get written into the reaction, but in lab what will probably happen is we'd follow this up with H2O just to stepwise up our reaction, and the final product that we would expect to see would be this guy. Okay. And what we've done is our alpha halogenation. Because of the alpha position, we now have a halogen. So, relatively straightforward, and depending on conditions, we can either do this under acidic or basic conditions, but we do run into some issues that pop up along the way. And more interesting is we've got secondary chemistry that we can take advantage of after we've gone through and done these reactions. And that's mostly what our alpha halogenation is looking at. You won't see this be all that important right away. So both conditions go through and result in the potential for kinetic and thermodynamic products, which is an interesting concept. So let's go through and take a look at this. The reaction that we just drew out, there was no difference between our hydrogen source. Now we do have a difference, okay, because I added that methyl group. So if we run under acidic conditions, we do end up seeing both of these products. Now the question becomes, oh my gosh, okay, with two possible products, one of them's got to be the major. So which one is the major? That's a little bit trickier. So this is why we talked about our kinetic versus our thermodynamic. And we look at our two possible enols that can come out of this. We end up with, the enol where our double bond is most substituted versus the enol where our double bond is least substituted. Okay. And as we already talked about, the enol with the double bond being most substituted is our thermodynamic product. And in this case, thermodynamics is going to win out, and we would expect our primary product, whoops, I thought I stepwise that. Our thermodynamic, oh darn it. We expect our thermodynamic product to be the major product, and the kinetic product to be our minor. Okay. What does it mean by major and minor? Well, most of the product solution will be the major brominated species. We do still end up with mixtures, so there's very little we can do about this. We do end up with both products in it. That's just kind of the way it works. So right off the bat, we're going to lose some yield because the bromination is going to happen in both possible places. Just going to happen larger in the major position. If we run it under basic conditions, you'll notice that we still have the potential for kinetic versus thermodynamic, but I changed the structure again just to tweak it up a little bit because we now do not have alpha hydrogens at the other position, which means only one hydrogen can be eliminated. And we end up with this product. So, well, that's kind of boring. Why would you go through and do that? Well, we went through and did that because now we want to take a closer look at our product. Okay, our product still has an alpha hydrogen. And this is our key difference between our acidic and basic conditions. Under the acidic conditions, we still have an alpha hydrogen, at least from our kinetic product. That alpha hydrogen could potentially react again, but remember, it's not super acidic at this point. Okay? The only reason it becomes acidic is because we've acidified our carbonyl, okay? And it kind of polarizes that bond enough, and we can get some formation of the enol. If we run under basic conditions, we are actively pulling off that hydrogen. So if that hydrogen is now more acidic, what happens? It's going to get pulled off quicker. Well, let's take a look at our basic conditions. We still have that pulling effect of our carbonyl, pulling electron density away, and we now also have a pulling effect of the bromine. The hydrogen, the alpha hydrogen, is now more acidic than it started. Okay? We go all the way back to the beginning. Our starting alpha hydrogen is less acidic than our product alpha hydrogen. Okay? We've seen issues like this pop up before. What does that mean? That means under basic conditions, you will almost always see halogenation. Okay? Acidic conditions will allow for monosubstitution, but we're almost always going to see polysubstitution in the case of our base conditions because our product, after a single halogenation, becomes more acidic than we started with. So we end up seeing more reactions happen under base conditions. So depending on what you're trying to do, you may want to run under acidic conditions, or you may want to run under basic conditions. So we got to be a little bit careful about that. And that decision is ultimately going to come down to what are we doing after we've done our alkylation, or our, not alkylation, our halogenation. And that's pretty much what this next slide is. So I'm going to leave this to you, play around with a little bit. I'll give you about 5 seconds here. Then I'm going to pause the video. And then I'll come back and we'll move on to a couple more problems to talk about. All three of these have kind of some interesting dynamics with them. So it may be a little bit of a challenge to pick up these products on your own. The activity, we'll walk through them a little bit slower. So and we're back. I'll just go ahead and mention what these things are referenced as. That first reaction is known as the Haloform. I'm not sure I remember that one actually, what the name is. I think it's Haloform synthesis, something along those lines. The next one, what we actually do is an elimination reaction. And in the last one, interesting, we actually go through and do a substitution reaction. And you may be thinking, what? That doesn't make any sense. Okay, well that's fine. Don't worry about it. The activity will kind of step you through what's happening at each of those phases, and I'll ask kind of important questions about what's going on with each of those. And the Haloform, that one's kind of weird. Just because I gave you reactions for the other ones. We get a substitution, or halogenation, and we get substitution again. Okay, so kind of odd. You go forwards, or you go forwards, backwards, and then forwards. Kind of weird. So last reaction is probably the most important one on this list, which is why we're going to come back to it. Methyl ketones can be converted into carboxylic acids. And this ultimately comes back to that concept that we already mentioned, that under basic conditions, when we try and run our halogenation reactions, so notice that we have a strong base here, that we cannot stop the reaction at one bromine. It actually goes through and does it multiple times. Okay, so what we end up with as an intermediate, I don't remember if I've got it actually drawn nicely on here or not, we end up with this guy, okay, with 3 bromines on it. This is an interesting substituent. It's actually a fantastic leaving group. And this is because all of those electronegative halogens are pulling that electron density away. So kind of a neat concept. With this being a reasonable leaving group, we can now run under acidic conditions, and water can come in and attack and kick out that good leaving group. That good leaving group can then pick up a hydrogen from the acidic environment, and we end up with our carboxylic acid and HCBr3. Okay, so kind of neat. Where it's kind of more important is that if we did this with iodine, what we've got is what's known as the iodoform test. So in general, if we use any halogen, it's the haloform, but the iodoform is a little bit more crucial. And this is something that does typically show up on the ACS test. They may not give you all this information, but they will ask about, to some certain extent, a yellow solid. This yellow solid is the iodoform product. So it's that HCI3. Okay. Well, this reaction really only works if we have a CH3 next to a carbonyl, okay, also known as a methyl ketone. So if a methyl ketone is present, we can form that really good leaving group with our carbon XXX, and we can run this reaction into the carboxylic acid. But typically what this is used for is not for the functional chemistry of turning it into a carboxylic acid, but that if you do this with our X's being iodines, this species is highly insoluble, and what ends up happening is you get this precipitate. And not only do you get a precipitate, but it's a nice, bright, brilliant yellow precipitate. So it's really used as a way to identify the presence of a methyl ketone, which seems kind of stupidly specific, but that's the intent behind this. All we're trying to do is say, oh, that means in this unknown solution, if I mix hydroxide and iodine, and I see this yellow precipitate, that, hey, I know I've got a methyl ketone. That's about it. So on the ACS test, what you might see is the question shown below, and they might go through and give you a whole bunch of different structures. So let's draw out some structures here. Give you, say, maybe acetone. They give you, what's that, pentanone. Might give you an aldehyde, okay, an ethyl aldehyde, and maybe they'll even give you carboxylic acid. Okay, and say, okay, what's your answer? Well, the only one that gives you a methyl and a ketone is in that first choice, and that would be your final answer. Okay, so it's used to identify particular functional groups, and that is pretty much the end of it on what we use it for. As far as lecture goes, I might play around with it and see if we can't use it to do a form of carboxylic acid and maybe do something with that acid. I don't know. More than likely, you'll just see it as a question of which of these is the proper functional group. And that is it for our halogenation reactions, I believe. So we'll go ahead and stop it there. Look, only 52 minutes, not that bad. And I will see you when I get back.